Hello and welcome to our expert webinar. Today it's all about Hitachi Energy's high voltage IGBT modules for demanding applications. My name is Erik Rehmann and I'm marketing manager at GVA in Mannheim. Our technical presentation today will be given by Virgilio Botan. Virgilio is global product manager for the BIMOS semiconductor products at Hitachi Energy in Lenzburg, Switzerland. This webinar is part of our expert series in which we are happy to share our knowledge and that of our partners on new products, technologies and findings from the field on a regular basis. Also check out our website gva-power.de and register for the webinars that interest you. Or simply visit our YouTube channel and watch the video recordings at a later time. During the live webinar, please feel free to use the chat function of our online portal and ask your questions. We will be happy to address them after the presentation. But now we go live to Virgilio Botan in Lenzburg. Virgilio, I hope you can see and hear us well.
Yes. Can you hear me, Erik?
We can hear you, and you just have to switch on your camera.
Yes, I'm working on it. Just a second. Camera.
Now it works.
Okay.
Welcome.
Okay, so welcome everybody also from my side. Thanks, Erik, for the introduction. So once again, I'm Virgilio Botan, product manager for BIMOS products, what we call BIMOS products. And I'll give you a short overview today about what we at Hitachi Energy been doing in the last years and what we are doing in the coming years to give and to present to our customers and to you better and more reliable products. Okay, so we can start. So the first I want to give an overview of our products. These are the products that we at Hitachi Energy offer on the market. I hope you can see my pointer. So we have what we call bipolar products, so classical press spec thyristors and diodes, and then IGCTs, which can be used in voltage source converters based on thyristor technology. And then we have what we call BIMOS products with the HiPAC and now the newest modules, the LinPak, press spec IGBTs with our name StackPak. And later on, we develop also industrial modules, low pack, 62 pack, and modules for EV. So this is our offering in a short overview, which goes then in a lot of different application, as you can see here in the middle. So from grid application to industrial, renewables, and of course, now more and more in e-mobility. If we then look more in detail at what we call BIMOS products, here's a short overview in terms of current and voltage on our offering. We can see the StackPak with high voltages, 4.5, 5.2 kilovolt, going very high also in current availability, up to nowadays 3 kiloampere, in the future even more. And then we have the HiPACs from 1700 volts, 6.5 with these current ratings, and LinPak trying to cover the same broad of voltages Of course, the LinPak being a smaller module, a little bit less current rating. And then we have the industrial modules like low pack, 62 pack, and the EV modules, especially for 1200 volt and lower. What do we do when we want to develop a new product? So we have the so-called technology curve. So the curve between the switching losses and on-state losses. And we try to optimize on this curve based on different requirements and different application. For topologies like MMC, where we have multi-level, the switching frequency is rather low. So the application benefits from a product that is specially optimized for low on-state. And then we have on the other side the classical two-level system where the switching frequencies tend to be higher to get a better sinusoidal, less harmonics, less disturbance, and then the application benefits from products from semiconductors which are especially optimized for low switching losses. So this is where we move on this so-called technology curve, and when we develop a next generation, we move the whole technology curve in this direction. So we have for the same, let's say, switching losses a much lower on-state, or the other way around. We improve for the same on-state the switching loss, or both of them in the same time. This in turn has a consequence on the output current. So the lower the switching losses, of course, the higher the output current for a given topology, for a given footprint. And you see this optimization between low on-state and low switching losses. So depending on frequency, the output is higher or lower. And then when we have a new technology curve, we move all this curve higher. In case of silicon products, we always have switching losses, rather high switching losses, and as a consequence, at high frequencies, this current output bends strongly down. And this is where the new class of semiconductors, like the wide bandgap semiconductors, are filling this space where the current output is still quite high, even at high frequencies. If we take a look on our chip technology development, starting from planar non-punch through and soft punch through devices, and then going to then enhanced planar, where we optimize the front side and the plasma, and on next to the emitter, and then going to trench technologies and what we see coming in the future, where we combine the trench cell with a reverse conducting IGBT, what we at Hitachi Energy call a BiGT, or bidirectional IGBT, where we integrate the freewheeling diode in the same silicon or in the same chip with the IGBT, always increasing current density and reducing losses. And this has as a consequence, as you can see here on the current output versus frequency, always an increasing slope, depending with the evolution of different chip technologies. If we look at our latest development in high voltage, it's the chip technology that we call SPT plus, of punch through plus, where we enhance the plasma distribution. We have for the 6.5 kilovolt in this type of package, which we call HiPAC or HiPAC 2 package. We have for 6.5 a rating of 1000 ampere, which we developed in the last couple of years, and we achieved this by working on the silicon to improve silicon specification. On junction termination, made the junction termination even in tighter. We add a peak collector on the backside to decrease the leakage current, and all in all, we increased the current rating. We also increased the junction temperature. So the previous generation was 125. Now it's 150. The same we did also for the diode. So we made the diode from our previous generation into an FC diode, made in much softer. FC stands for field charge extraction. So we have the diode in the latest part of reverse recovery, where the field touches the backside. We have further injection of carriers to make this last part of the recovery much softer. And all in all, when we put this into the chipset, we have quite a big performance increase. You see here the curves of current output versus frequency. For the previous generation, the standard 600, 750 amp in this package versus now the 1000 amp. So this is improvement in inverter mode and in rectifier mode, where the diode is more used. The same type of improvement we did also for our 4.5 generation, reaching a rating of 1500 amp. So as I said, similar kind of improvements of silicon and termination, and also here taking an FC diode to improve the softness, and then as an output, you see inverter mode, current output improvement, and the rectifier mode, what we can achieve with this next generation for 4.5. So these are of course used heavily in traction application, but also in medium voltage drives and also grid applications. Yeah. Now, if we look at our press pack IGBT, which we called stack pack, is what I like to call the strongest IGBT that there exists out there. It comes in this type of square package. It's heavily used in grid application where series connection is needed because the voltages are very high, starting from maybe from SVC or STATCOMs at 30 kilovolt, but going in HVDC stations up to 500 kilovolt. So series connection is needed, and the scalability of the stack pack nowadays is one of its selling arguments, because we have this modular approach where the stack pack is built with individual sub-modules, and we can scale current capability by taking different amount of modules. So we can have a stack pack with 3 sub-modules, with 4 sub-modules, and even as you see a drawing here, up to 8 sub-modules. So it has a very nice current scaling. It's especially done for series connection, and you can see here test done with a stack pack which is rated 5 kiloampere, switching 2 times nominal for two devices in parallel, so switching off 20 kiloampere of current with 2 stack packs. And I think it's quite impressive, and this is a module we see a great potential and a great future for it. If we move on from stack pack, going a little bit in a different direction for low voltage modules used mainly in industrial application, we have the 62 pack, 62 millimeter package. in different ratings. What we did, especially for 62, we looked at higher reliability for this module. We look at the terminals. We have this so-called spacer for terminals to make sure that the solder is very homogeneous around bending of the base plate to ensure also reliability and a good thermal contact over the whole lifetime. And spacers also for substrate soldering to make sure that we have a stable solder or stable contact over the lifetime. So we took all the learnings that we had in high power, where is our, let's say, our traditional field where we have experience in traction application, grid application, and we implement also now for this industrial modules. You can see also in terms of robustness, this 1700 volt RBSOA, they switch 4 times nominal at 175 degrees without problem. Also in terms of short circuit capability, at 175 full 10 microseconds that we are used to especially in traction application. We have this classical 10 microsecond short circuit capability. Moving on, different class of products like the LinPak, similar situation as for the 62 millimeter modules. We have here 2 voltage classes, the 1700 volt, the 1200 volt, with different current ratings. In terms of what we put inside to make the module very reliable and stable is very similar. So spacers, we take great care of the pre-bow of the base plate. We have now for higher current modules, we have extra copper bonds to ensure the current carrying capability, and also we offer the option with thermal interface material for, again, more reliable and constant thermal interface between the module and the cooler over the lifetime. Also here in terms of capability, RBSOA exceeding the data sheet value. So here you see 3 times nominal switching on the 1200 volt. The same for short circuit. I'll not go into details. For the 1700 volt 175 operation, even a higher margin with 4 times RBSOA, 4 times nominal current capability. And the same for short circuit up to 10 microseconds for the 1700 volt. If we now move forward to yet a new class of power semiconductors, the LinPak. I call the LinPak the new IGBT standard, because we see the LinPak was released, I think, by us as the first company that had this in commercial offering already 6-7 years ago. It starts, or it is already a standard in traction application, but now slowly it's becoming also a standard module more and more in also industrial application, renewable, and so forth. Right now the offering in terms of current and voltage looks a bit like this. So from 1700 volt to 6.5 kilovolt, 1700 volt up to 3.3 in this type of package, what we call low voltage LinPak, with isolation capability up to 6 kilovolt, and then another package for 3.3, 4.5, 6.5 kilovolt IGBTs, or we'll see later silicon carbide, with isolation capability up to up to 10 kilovolt or 10.2 kilovolt. And in the next slides, I'd like to show a little bit more about what we do in the LinPak. And I'll start with an update of the high voltage LinPak. You see here blown up mock-up of this module, how it's being built. What we will use for high voltage LinPak is a similar technique that we have for the used for the that we developed for the low voltage package, which is we ultrasonic weld the terminals for higher reliability. These packages for low voltage, but also for high voltage, they carry more and more current with the improvements of chip and reduction of chip losses. So more and more current is needed, and we see that slowly the terminals start to be a bottleneck. So that's why we weld these terminals. In the ultrasonic welding process, particles are being created due to the high temperature, which cannot be avoided. I know some of our competitors wash the modules afterwards to remove these particles, because they can be very, very dangerous, especially if they sit on the chip or in between on the isolation paths and so forth. What we have a technique, we call it an air blade. So we blow air from the sides at high pressure, and we have a comprimation area where this air is even more squeezed together to increase pressure and speed below the terminals, and then it reaches the place where the ultrasonic welding is happening, and by then is really blowing out all the particles that are being created in this process. Which is a very nice and neat technique to ensure that we don't have any hot particles laying around and gluing or on different areas of the module. In terms of voltages, here I show some switching curves for 6.5 kilovolt. The 6.5 LinPak will have a rating of 300 amp, and here's some switching curves at 2 times nominal, turn on, turn off. See that behaves very nicely. Also comparison between top side and bottom side. It looks very nice. The same in terms of SOA, short circuit SOA in cold and hot. We have the very nice capability, 10 microsecond, that is, as I said, mostly required for traction application. So it looks quite good. Then moving on. From the 6.5, we go lower in voltage class towards 3.3 kilovolt. For the 3.3 kilovolt, we have already a module out there in the low voltage. We have a first generation, which is based on the SPT plus chip technology, and now we are working on a 3.3 on a second generation chipset for the LinPak. And this will be based on a trench enhanced planar chip technology. And here we will offer for different application 2 different variants of this chipset. One with low on state, so for MMC or multi-level topologies where the application benefits strongly from lower on state. And then we'll have a higher a module where it's more optimized for the switching losses for classical application like the two level topologies. A little bit of switching curves, and that we see here is RBSOA, also 3 times nominal, so very strong performance. A short circuit, just wanted to demonstrate capability. We see that we can do short circuit even 20 or above 20 microsecond, which is quite impressive. In terms of diode and diode softness, that allows us also to switch faster and then optimize switching losses, terminal losses. We have, again, very soft diode with our technology concept of field charge extraction with the islands on the backside. And you can see here a scan through different temperatures and different driving conditions. So we are overall, we maintain switching over voltage below the nominal voltage, and have quite a soft diode. Now, so we went from 6.5 lower to 3.3. With 3.3 kilovolt, we can use both in high voltage package, but also in low voltage LinPak, and now moving even further to low voltage 1700 volt. As I said, for low voltage, we have modules out there since 6-7 years. The rating that we used to have was one, and we still have, is LinPak with 1000 amp, and now with the new chip technology, we want to move from the 1000 amp rating to 1500 amp in the same package, in the same footprint, by improving the loss, or reducing the losses of the chip, and have some slight modification on the package to allow this higher rating, to allow better current carrying capability, and better thermal stack of the module for the module. Yes. So here, just want to point out a couple of characteristics. So this is where our SPT++ chip sits in terms of technology curve. So turn-off losses versus on state, and this is where we are moving with different variants that we are studying right now, strongly into improving the technology curve, as I showed in the beginning. This for IGBT, and the same for the diode. We go for an ultra thin diode, where we improve the losses considerably, to allow, as I said, in the same footprint, for a much higher rating. Here also some switch characteristics, like SOA room temperature, or 175. Short circuit SOA, and we see that we have the capability that we require for this module. Also RBSOA, looks like we here almost close to 3 times nominal, so it looks like no problem, quite a robust chip here. And as we discussed in the beginning, we have for the silicon in terms of, when we look at figure of merit, current output versus frequency, at the higher frequency we pay a small penalty for the switching losses. So due to the switching losses, the higher the frequency, the lower the output current. And this is what is addressed when we go to silicon carbide. We have the output at higher switching frequencies, much higher, and this is due to much lower switching losses. See here a comparison for a 3.3 kilovolt LinPak that we have in a low voltage housing, the silicon compared to silicon carbide in different conditions, a hybrid module or a full SiC. And also for the full SiC, it's very important how fast one can drive this module. And you see here some switching curves for the 3.3 silicon carbide. This is how the substrate looks like with quite small chips. So the chips nowadays they tend to be the range of 5 times 5 millimeter or slightly bigger. Not yet the size of normal IGBT chips, due to, of course, defectivity that we still have on these wafers and yield optimization, which then imposes a lot of challenges in how to build this substrates, having all this gate connection, distribution of the gate connection, and source or emitter, in order to make it more homogeneous and have all these individual chips switch as good as possible, as harmonious as possible together. But this is what I think we manage quite well, and you can see here in the switching forms, and also let's say controllability. You see here in this graph switching energy, which of course comes from changing DIDT and switching speed with the RG, with the gate resistance. So we can control it quite well. But even at faster switching, if we take a zero external gate resistance, we can still have an acceptable switching performance. And if you compare these numbers in terms of switching losses versus silicon variant in the same footprint, one sees that for similar switch current, we have factor 10, close to factor 10 lower switching losses for silicon carbide compared to the silicon equivalent, which is quite impressive. Silicon carbide, of course, this is 3.3 that I showed in the previous slides, but one of the promises of silicon carbide is also higher voltages. We are also developing a 6.5 kilovolt silicon carbide, thinking of traction application, but more in the direction of grid, where we have a lot of series connection of nowadays of IGBTs, and this will profit a lot if we'll have per semiconductor a much higher blocking voltage. So that's why we look a lot at higher blocking voltages, like 6.5 kilovolt. So you see here some switching events of modules of chips that we produce inside in our factory here in Switzerland, and even going forward to even higher voltage classes. We made some 10 kilovolt devices that we switch and we see how to produce them. Of course, this much higher voltage classes like 6.5, 10 kilovolt, they come with their own challenges in terms of ground material and, as I said, defectivity of this epi wafers, but also in terms of packaging, isolation, and so forth, and junction termination. So this is work that we do to that we see that will come in the next maybe 3 to 5 years, or 10 years. But we need to prepare for this new developments, because silicon carbide is providing this opportunity to go in this direction. As an overview of the silicon carbide modules. As I said, we offer it in low voltage LinPak, but also nowadays in high voltage LinPak. So high voltage LinPak silicon carbide starting with 3.3 kilovolt, going to 6.5 kilovolt. We have usually two current rating, where we fully populate the substrates or half populate this substrates. So usually two current rating for voltage class, and nowadays we concentrate in our factory mostly on 1200 volt, 3.3, 6.5 for different application. 1200 volt especially for automotive, 3.3 for industrial and traction application, 6.5 for traction in grid. But we see more and more the demand for 2.3 kilovolt, 1700 volt. And other voltage classes. As a conclusion to the overall, let's say, portfolio, this is the products that I presented to you. For all of them, we are trying to increase current rating in same footprint. So you see for the LinPak, also 1700 volt from 1 to 1500 amp, 1 kilo amp to 1500 amp. Also for the same for 3.3 stack pack, as I showed, is going towards 5 and 6 kiloampere. So what we do is improve the chip to reduce losses and get more current out, but also improving the modules themselves to get lower thermal resistance, better connection, where in application we are very let's say power cycle sensitive or require long lifetime. And look also at new packages, like as I mentioned, nowadays the LinPak, and also in the space of low voltage modules, what kind of different package suits best the application. Yeah, so I think with this I conclude my my presentation as an overview of our products, of what we did in the last years and what we plan to do in the coming time. Yeah. And if there's any question, I'll gladly take them and answer.
Yeah. Thank you very much, Virgilio, for this interesting presentation. This brings us to the question and answer session. You now have the opportunity to formulate your open question in the chat. Please make active use of it. And while our guests have time to type their question, Virgilio, I would have some questions from myself. One more general question would be, how do you see the future of the high power SiC modules?
Yes, as I presented, we have in development silicon carbide in high power modules. So we have first, of course, EV modules. I don't know if you call them high power or not, but EV modules, they already have some hundreds of amps rating, up to 700, 800 to 900 amp rating. But then moving to more even higher powers for train or traction application or grid, solid state transformers. There's more and more, let's say, more and more discussion about using such modules, because there's application where there's a high benefit of reducing switching losses. For instance, in traction, we have nowadays more and more the hybrid trains, the trains that need to operate also from batteries or hydrogen fuel cells or so forth. And then they have usually a DC-DC converter, where there's a direct benefit of going as high as possible in switching frequency. And I think starting with this, it will be the first place where such modules would use a direct use. And with time, as of course we are all aware, cost is still an issue for silicon carbide. I mean, silicon carbide has very nice properties, but still cost is a little bit coming as a barrier of larger adoption of these modules. With volumes of scale, especially from automotive, but also from other industries, we will manage to reduce cost and then see a much larger adoption of this new technology, which is very promising.
Okay, thank you. Speaking about the commercial issues, are voltages higher than 3.3 kV viable for commercially viable for SiC?
Yeah. So right now, of course, it's us, but also I guess also some of our competitors look at this. As I mentioned also in my presentation, especially having in mind grid applications where we talk about hundreds of kilovolt or tens and hundreds of kilovolt. So where series connection is necessary. Of course, there would be a big incentive to use semiconductors at much higher voltage rating. What we have nowadays, I mentioned also for industrial voltages like 3.3, and so is the cost of the ground material of the epi wafers. You can imagine the higher the stack of the epi layer, the higher probability to have stacking faults and other defects. So as we get better and better in producing this material, I'm convinced that the cost also for very thick epi layers will decrease, and then at some point, especially maybe in the beginning for niche application, we'll be able to see the justification of having such modules in use. But until then, as I mentioned also before, there's still problems to be solved, like how do we do junction termination for such high voltage classes? What kind of modules will we have with that can take the isolation voltage, and so forth. Yeah. So there's still challenges ahead. Yeah.
Mm-hmm. Okay, thank you. A third question, what is the adoption of the new standard module, the LinPak, into different applications?
Yes. So as I said, at Hitachi Energy, I think we were the first or one of the first to have this module really in commercial use back in 2015, 2016. And it started, I think there's no secret with traction applications. So we saw some traction OEMs going for this type of footprint. And by now we see it more or less for all the big traction inverter manufacturers, the move for their next generation converters to use this type of modules. What has happened, I think, in the last 2-3 years is that we see also a lot of what we call industrial customers. By industrial, I mean low voltage drives, solar, battery storage, and wind, and so forth. Inverter manufacturers that look more and more seriously at this type of package, also for the next generation. Sometimes replacing smaller modules, not to have to parallel as many, like a low pack type of module. Sometimes replacing also, let's say, equivalent rating modules like we see on the market. Because this package is so versatile, the LinPak package with very low strain inductance, very good paralleling. So you have a building block that you can build up different current ratings with it. And then also voltage scalability. So we will see these packages everywhere from 1200 volt to 6.5. Of course, one package, let's say up to 6 kilovolt isolation. So from, let's say, 1200 volt IGBTs or silicon carbide to 3.3. And another footprint from 3.3 to 6.5. But in terms of unit, one package of the whole voltage range, which with very low strain inductance, very good paralleling capability, and then of course silicon carbide ready. So I think there's a lot of advantages for our customers in this type of package. So I'm convinced that this will see a very large adoption in the coming years in all sorts of industries.
Okay.
In application.
And a question about the cooling of LinPak. Does, in your point of view, the LinPak with direct cooling, for example, with this pin fin, make sense?
Yeah, so we see, especially in automotive, we see a lot of packages that have direct cooling or pin fin, and this is then done for to have the optimum cooling of the device, to squeeze as much power out of the device as possible. This is of course the best use of the semiconductor. Of course, is a performance that does not come for free. So this implies that our customers need to optimize their cooler. So they have to make sure that there's no leak, and then have this mounted very careful. So it gives a little bit of extra challenges to our customers, but the benefit is also very big. And personally, I see the adoption of such a concept, especially for silicon carbide, where we have this very nice semiconductor with very nice properties, and then the packages which are especially for very high powers, like we have the LinPak or other packages, they are a little bit slowing the module down or not allowing to get the best performance out of this very nice semiconductor. So there, I think it will start by using this pin fin concept, try to use the best, because we already have a very expensive part, which is the semiconductor in the module. And it makes sense to also, from modules perspective and integration of this module, to spend a little bit more on how we integrate this semiconductor in the overall inverter to make the best use of it. So I think it will start with silicon carbide, where it makes a lot of sense, and maybe with time will spread also to other semiconductors, and also to silicon.
Okay, thank you, Virgilio. There are no further questions in the chat so far. This brings us to the end of our webinar. If you still have any questions, please do not hesitate to contact me or my colleagues from sales directly, and you will receive an email with the contact details of our responsible employees afterwards. As experts in power electronics, we at GVA have, of course, even more to offer than semiconductors. In addition to the sale of a whole range of power electronic components, we develop and manufacture assemblies and systems entirely according to your specifications, usually in the range of a few kV up to the megawatt range. Feel free to visit our website for more information. The best way to follow us is on LinkedIn. This is the fastest way to find out the latest news about GVA and its partners, as well as about our latest expert webinars. Virgilio Botan and I thank you for your interest. I would be happy to welcome you back at one of our next webinars. Take care, goodbye, and hopefully see you soon.
Thank you. Bye-bye also from my side.